Hi and good afternoon. We continue with the second part of chapter 2. Okay, so now we go into the clippers. So clippers are network that employ diodes to clip away a portion of an incoming signal or input signal without distorting the remaining part of the applied waveform. So that means we have part of the signal is being cut off or being clipped away. So we have diode in clipper circuits which will limit positive or negative input voltage to a respective value. So this one is specifically used with alternating input. We can have either in sinusoidal form, we can have rectangular, or we can also have triangular and so on, as long as it is an alternating input. So it has two types. We have a series clipper and we have a parallel clipper. For a series clipper, diode in series will clip a portion of AC input waveform, and the only voltage that put the diode in forward bias can pass through the diode. Input voltage that put the diodes in reverse bias will be clipped. So that means, okay, whatever the input voltage that can cause the voltage to be less and then the value of the diode, or put the diode in reverse bias, it will be clipped away. Okay, so we have two types, with DC supply and without DC supply. Okay, if you remember, without DC plus is similar with the bridge rectifier, and also we have a center tap rectifier. Okay, this one is without DC supply. Okay, so if you can see, if you recall what you have learned before, okay, for the series clipper without DC supply, okay, there is no DC supply in series with the diode. The diode clip a portion of the AC wave. Okay, for example, if we have a square wave here something like this, we can have positive that will pass through and the negative will be clipped away. For a triangular wave, we have positive and negative input, and this is the part that been allowed, and the negative part is being clipped away. So the diode clips any voltage that does not put it in forward bias, and that will be a reverse bias in polarity and a voltage less than 0.7 volt for a second diode. So similar also, if we use the germanium diode, the voltage less than 0.7 volt. Okay, so this is a series clipper circuit with DC supply. So it opposes and applied voltage in the first half cycle. So this is the input voltage. It is actually the alternative voltage. Okay, this is the V, the DC supply, and this is the output voltage here. Okay, it depends on the value of V actually. Okay, so first we need to determine the transition level for a circuit. The transition from one state to the other. That means either it change from off to on or on to off. So we use this formula: V equal Vi plus V equals to 0, Vi plus V equals to 0. So that means we want to determine the transition level, okay, the boundary between the off state and the on state. Okay, at this point, at this juncture, the value of V out equals to 0. So that means when Vi plus V equals to 0, Ui is this one and V is this one. Okay, it will make the voltage to be also equals to 0. Because why? Because the value of Vi and V is in opposite values. So that means it will cancel out, so that there is no voltages inside the circuit. So when there is no voltages, there is no current flow here. So D or I R will be also equals to 0. So ID, remember that ID is also equal to IR, the current across the resistor. So when ID is 0, IR is also 0, and we know that V out equals to IRRR. So that means it will also be 0. Okay, so we have a sinusoidal waveform. Okay, using the transition voltage to determine or to define the on and off regions. Okay, so this is the transition voltages that we want to determine. Okay, this will determine whether this is on, and the below of the region will be off. So that means when it is on, okay, this is the allowable part, and when it is off, this is the part that will be clipped away. So this is a circuit. We have again, okay, this is VI, this is V, and this is V out. So this is a for a clip with DC supply. So I mean we have the diode in series. Okay, this is the diode here when it is conducting. So when the diode conducts, it will be similar to a short circuit. Okay, so sketching the waveform of V out, V naught using the results obtained for V naught above and below the voltage transition level. Okay, this is the voltage transition level. Okay, so the part that will be allowed through to the diode is this part, and this part will be clip away. The value is similar to equals to Vm, here Vm minus the value of V here. Okay, so this is the part that will be clip. For an example, if we have a sinusoidal waveform here, and the maximum value is 20 volt AC. Okay, remember this is AC supply, the AC input, and this is the DC supply. Okay, 5 volt DC. Okay, so by adding a DC source to the circuit, the voltage required to forward bias the diode can be changed. Okay, so as long as we change the value of V, we can change the boundary, we can change the transition level to forward bias the diode. We need to determine the transition level for the clipper. So remember this formula. In order to determine the transition level, we must have V out plus V equals to 0. So in this case, Vi plus 5 volt DC supply equals to 0, and this will in turn give Vi equals to minus 0 volt. And at this point also, you must remember that V out is also equals to 0. So this one is the boundary level. So that means we have a sinusoidal waveform. This is 20 volt, and this is say minus 5 volt. Okay, so this will be the transition level. Okay, so that means this transition level, this is the part that will be allowed, and this is the part that will be clipped away. Okay, so this is actually a graph of this is the input voltage versus the time. And this is input, and this is the graph of output versus time. So remember that the first we need to determine the transition level. Okay, the transition level will give you Vi equals to minus 5 volt. Okay, which is here. Okay, this is the transition level. Okay, and if you follow the Kirchhoff voltage law, whereby okay, Vi plus V will give you the value of the output voltage. Okay, so now in order to determine the upper portion which is being allowed to pass away when the diode is in forward bias, okay, we have 20 plus equals to V out, and V out equals to 25, which is here, and the other is okay when the value of input voltage is equals to 0. Okay, that means Vi plus V equals to V out. Okay, 0 plus 5 equals to V out. V out equals to 5 volt. Okay, which is this one. Okay, so that means when you plot the output voltage, you will see something like this. This one, this is the output. This is the input, and you will see the output here. Transition level. If we plot, okay, we plot here from, okay, V out equals to 0 here. Okay, this is the first part when we determine the transition voltage. Okay, whereby you know that at this part, remember again, Vi plus V equals to 0 and equals to also V out. So that means negative 5 plus 5 equals to 0. Okay, so that means the output voltage equals to 0, which is here. Okay, so when you plot, you have three values. You have V out equals to 0, you have V out equals to 5 volt, and also you have V out equals to 25 volt. Okay, this one is actually the transition. Sorry. Okay, this is the transition. Okay, so when you plot, okay, this is the upper value, and this is the lower value. Okay, so that's why you have this type of graph. Okay, now what happens if we replace the sinusoidal waveform with square wave? Okay, we have the sinusoidal waveform with 20 volt AC. Okay, now we have also the square wave with 20 volt AC. Okay, so this is something like this. Okay, this is 20 volt. This is minus 20 volt. Okay, what will happen is when you have 20 volt, you have 5. Okay, so this is enough to forward bias the diode. So when the diode is forward bias, it is in on state or short circuit. So you will have, okay, something like this. Okay, Vi equals to 20. Remember again, Vi plus V equals to V out, and then 20 plus 5 equals to 25. Okay, which is this. Okay, now, so when the sinusoidal waveform is in the second cycle, so in the second cycle it is a negative cycle. So now let's say in the negative cycle, the second part of the cycle, okay, it is at a value of minus 10 volt. Okay, what will happen is minus 10 volt, you plus with 5 volt equals to minus 5. Okay, minus 5 volt here, it is not enough to forward bias the diode. So that means this diode will act as an open circuit. So the value here will be 0. Okay, the output value will be 0. So that means in the second cycle, the second half cycle of the sinusoidal, of the square wave, this one will be 0. So this is the actually output that you can see, 25 volt, and after that is 0. Okay. what happened if we have a parallel clipper? In parallel clipper, we have the diode which is being put in parallel with the output. Okay, so by taking output across the so this one we take the output across the diode. So the output is now the voltage when the diode is not conducting. Okay, so that means when the diode is not conducting, it is actually an open circuit. The value of V out will be equal to V in. Okay. So this one is also similar to the output from the bridge rectifier, whereby you can have something like this. This is the input. You can have positive being clipped away and the negative part being allowed, okay, depending on the position of the diode, the direction of the diode. Okay, so if you have a triangular wave here, okay, this positive cycle is being clipped away and the negative cycle is being allowed to pass. Okay, for example, if we have this triangular wave, the value is 16 volt maximum and the minimum value is minus 16 volt. Okay, so this is the input voltage here. Okay, and we have the direction of the direction of the diode is here, pointing upwards. Okay, what happened is it means that okay, this diode will only allow the negative cycle to pass away, to pass through. So the positive cycle will not be allowed to pass through. So that means we can have something like this. Okay, this is positive, this is negative, and this part is being clipped away. Only the negative part is being allowed to pass. Okay, so the transition level depends on the value of V. Right, first we have to determine the transition level for the circuit. So the transition level, we can take it as when the diode is in uh, on state. So that means when it is in on state, the diode will be a short circuit. So when it is so, Vd equals to 0, so we will have V out, which is equals to the value of V equals to 4 volt. Okay, so this is the transition level between the off state and the on state. Okay, so first we need to determine the value of V out or V naught for the open state of the diode. So when it is open here, okay, it means that the diode is not conducting, so it is in reverse bias. Okay, so that means when it is open, so the value of current here will also be 0. I can say that if we have IR equals to 0, and if we have PD, which is also equals to 0 because there is an open circuit here. So the circuit is not open, so there is no current flow. So when this happens, the value of V out will also be equal to the value of the input voltage. Okay, so what happened for the negative region of the input voltage? So when we know that the diode will conduct the negative cycle, so that means this one will be short circuit. So when it happens, we will have the V out here, which is uh, or in parallel with the value of V. So that means we will have V out equals to V equals to 4 volt. So that means for the rest of the negative cycle, the value of output will remain at 4 volt. So this is a fixed value, so it will be not more than 4 or less than 4 volt. Okay, so this is the output sketch. Okay, this is the input voltage versus the time, and this is the output voltage versus time. Okay, so this is the positive cycle. So when the diode is not conducting, and this is a negative cycle when the diode is conducting. So when the diode conducts, it will remain at volts here, and when the diode does not conduct, it will follow the shape here. Okay, this is the transmission level. So if we draw a straight line here, and this is where the diode is not conducting, so it will follow the same shape with the maximum value of 16 volt, and it will be at a minimum value of 4 volts. So the output will be between 4 volt and 16 volts. So if you see this one, okay, there is no negative cycle, no negative cycle. Okay, because we have already supplied the circuit with 4 volt DC voltage in parallel with the output. Okay, what happened if we introduce the approximate model of the silicon diode? Okay, remember that when we use approximate model, we will introduce also the voltage drop of 0.7 volt for the silicon diode. Okay, so that means we have to take into account the 0.7 volt. So that means because the sign is this is positive, this is positive to positive. Okay, the positive supply, and the diode is reverse in the opposite direction. So the output voltage V out will be 4 minus 0.7 volt, which is 3.3 volt. Okay, so that means you will have the transition level, which is also different. We have to take into account voltage drop or knee voltage 0.7 volt. Okay, so if we take into account this to determine the output voltage for the network while the diode is on state. Okay, when it is on state, there's a voltage drop here. So that means there will be current flow for this direction. Okay, why? Because this is the negative cycle. So in negative cycle, the diode will conduct. Okay, so when we sketch, it's almost the same, just that the transition level is being reduced to 3.3. Okay, so that means I repeat again for ideal diode. So get up this one. Okay, for ideal diode, VD equals to 0. For this one, it's approximated diode. Okay, VD equals to 0.7. So that means we use ideal diode, the transition level is 4 volt. Okay, transition level 4 volt. For approximate diode, the transition level is 4 minus 0.7 equals to 3.3 volt. Okay, so as a summary, you can read to look through the output as the input for your understanding. Okay, this is a positive cycle, this is a negative. So just compare with one and try to look through the of the diode. This is the diode direction to the left. Okay, this is the diode direction to the right. So what happened here? Okay, so this is in the left direction. So the positive cycle will be clipped away, and this one, the negative cycle, will be clipped away. Okay, so this one for the parallel clipper circuit summary. Okay, you can see here in parallel circuit summary, the output voltage is taken in parallel with the diode and also the supply voltage. Okay, so just have a look at this. Okay, this is the downward direction. Downward direction, this one allow the positive cycle, and this is the upward direction. Okay, this one will allow the negative cycle. Okay, we can also have something like this. Okay, this is downwards pointing, this is upward pointing. Okay, for this one, it will allow the positive cycle to pass through, and this one will allow the negative cycle to pass through. So if we have two branches of diodes in opposite direction, we will have the output, the positive cycles being clipped away, and we can also have the negative cycle being clipped away. Okay, now we move to clamper diode circuits. Okay, a clamper diode circuit is a network constructed of a diode, a resistor, and a capacitor that shift a waveform to a different DC level without changing the appearance of the applied signal. It means that the waveform, the original waveform, will be shifted upwards or downwards. So it's only in a vertical shift. Okay, a diode in conjunction with a capacitor can be used to clamp an AC signal to a specific DC level. So for example, if we have normal sinusoidal waveform, so using a clamp circuit, it can be moved, in this case move downwards. Okay, you see that the shape remains the same, there is no distortion. It's only the difference is in the maximum value and also the minimum value of the output waveform. Okay, so in order for us to analyze the clamper circuit, first we start to analyze from the cycle either positive or negative when the diode is in on state. Okay, it depends on the position of diode, whether it is pointing downwards or pointing upwards. Okay, so that means if the diode is pointing downwards, it means that the diode is on in the positive cycle. And if the diode is pointing downwards, it is pointing um, it's turning on at in negative cycle. Okay, so the capacitor will be charged up. Use KVL to determine the voltage level of the capacitor and determine the output voltage. Okay, this is in the on state of the diode. So when the diode is in the off state, okay, first we assume that the capacitor holds the established voltage level, okay, from the on state. So that means the voltage level of the capacitor VC from the on state will be used or remain when the diode is in the off state. So again, you use KVL to determine the output voltage. The total swing of the output should be the same as input. Okay, the total swing here is the range of the maximum value and the minimum value. So if we have something like this sinusoidal, this is the swing. Okay, the swing or the range of the voltage. Okay, for example, you are asked to draw the upper waveform for the circuit below. We have a square wave here. The maximum value is 4 volt. The minimum value is minus 4 volt. You see that in the circuit, the is pointing upwards. Means that it is in on state. It will be in on state when it is in negative cycle. Okay, so the diode is on state at the negative cycle. Okay, then you apply KVL to determine the BC. Okay, so when the diode is on, we assume that this is short circuit already. So when this is short circuit, V out or V naught is equals to 0 because the current will bypass V naught. Okay, so we take the KVL from this anti-clockwise thing. Means we have V in minus VC. Okay, because VC is this is plus, this is positive. Okay, plus minus. So that means V in minus VC. Okay, there is no voltage, so equals to 0. Okay, and then we rearrange back. We will have V in equals to VC. Okay, what is the value of VC? The value of VC is equal to V in, which is equal to 4 volt. Next, you determine V naught. Okay, V naught, the output voltage, is equal to 0. So that means we have V in equals to 4, the output voltage is equal to 0. This is for the on state. Next, for the off state of the diode, when it is in a positive cycle, so the diode will be in off state, so it is an open circuit. So again, we do the KVL whereby anti-clockwise. Okay, V in here, V in, and then we minus V out. Okay, we plus VC equal to 0. Okay, we will have here V out equals to V in plus VC. So the value of V in is 4 and VC from the previous on state is equal to 4. So the output voltage will be 8. Okay, now we draw the waveform and make sure the total swing of the output is same as the input. Okay, so remember the total swing here between 4 volt and minus 4 volt is 8 volt. The range is 8 volt. 4 minus 4 equals to 8. Okay, so this is the range of the voltage. So when we draw, the same range must be applied to the output. Okay, now we will have the total swing input. Okay, 4 volt here minus, okay, plus minus 8, we have 8 volt, and then the total swing here, 8 volt minus 0 is also equals to 8 volt. Okay, this is the swing. So we know from the on state, okay, the output voltage is equal to 0. Now from the off state, the output voltage is equals to 8 volt. Okay, so remember again, the off state is in the positive cycle, so the value of the voltage at the positive cycle is 8 volt. And when it is in uh, off state, okay, when it is in, I repeat again, okay, when it is in positive cycle, it is off state, so the value of output is 8 volt. When it is in negative cycle, the diode is in on state. Okay, and then the output voltage will be 0. Okay, so you can see that you have 0 volt and this is 8 volt. Okay, next, draw the output waveform for the circuit below. Okay, this circuit, the maximum value is 5 volt, minimum value is 5 volt. Okay, the range here is 5 minus negative 15 equals to 20 volts. Okay, this is the voltage range. 20 volt is the range. Okay, now diode is pointing upwards. Okay, again, it is active or on state in negative cycle, and it will be in off state in positive cycle. So again, same as before, we apply KVL to determine VC. Okay, remember again, VC, this is the sign, this is negative, positive VC. Okay, anti-clockwise, we do the KVL. Okay, V in, this is the first loop, follow this loop. So that means V in plus V, okay, minus VC equals to 0. Because why? Because the sign of the VC is in opposite direction. Okay, so we will have VC equals to V in plus V. Okay, the value of V in is 15 and the value of V is 4. So we will have the output, the value of VC is 19 volt. Okay, so now we try to determine V out. Okay, V here is parallel to V, so it must have the same value. So V out is equals to 4 volt. Okay, so this is in the negative cycle. Okay, remember this is negative the value of the out is 4 volt. Okay, how about the positive cycle? The diode is in off state when it is in positive cycle. So again, anti-clockwise here, we apply KPL, we will have the V in, okay, minus V out plus VC equals to 0. We assume that the value of VC maintained, so that means 5 minus V out plus 19 equal to 0, and we have the output here is equals to 24 volt. Okay, so this is in positive cycle. So the value of the voltage in positive cycle is 24 volt, while the value in negative cycle is, again, so see you at the next slide. Okay, the value of the negative cycle is 4 volt, the value of positive cycle is 24 volt. The range here maintained, it is 20 volt difference. Okay, again, this one is also 20 volt difference. Okay, so we have made sure that the total swing of the input and also the output is the same. Okay, in positive cycle is here. Okay, this is for the input, and for the output is also the same. Okay, another example that I think you can try on your own. We have positive cycle, the voltage is 10 volt. Negative cycle, the voltage is minus 20 volt. So the range here is 20 volt range. Okay, so using the same as before, try to solve for this. I want you to try on your own first. Okay, try to understand this and this. Okay, and then we go to these variations of clamper circuits. Okay, for example, we have a sinusoidal waveform. Okay, and then we have another branch here. We introduce a resistor in parallel to the combination, the branch with the combination of diode and battery, and this is applied. So the input signal can be any type of waveform, either sine wave, square wave, triangular wave, etc. And you can adjust the DC clamping level with a DC source. The level of the clamping can be adjusted by a DC source. Okay, remember this one may not look symmetry, but in actual, this is a symmetry. Just that the DC level here is different. Okay, so this is how where the original signal is being clamped. It means that this is the input and this is the output. It means that the waveform is being clamped upwards. Okay, as a summary, you can see the direction here. Okay, pointing downwards, pointing downwards, pointing downwards. It means that the diode is on in positive cycle. On positive cycle, while this one is pointing upwards. Okay, it is on negative cycle. Okay, and then you can try on your own for the rest. Try to understand this. Next, we go to the practical applications of diode circuits. Okay, we have rectifier circuits, a combination for the conversion of AC to DC for DC operated circuit, and we can also have rectifier circuits for battery charging circuit. Okay, and then the simple diode circuits, we have protective circuits against overcurrent, polarity reversals, currents caused by any negative kick in the relay circuit. Okay, these are the two most common applications for the diode circuits. Okay, now we go to this diode data sheet. Okay, if you ever look at the data sheet for diodes and other devices given detailed information about specific characteristics, okay, we can have such characteristics like the various maximum current, the voltage rating, the temperature range, the voltage versus current. It's sometimes a very valuable piece of information because you sometimes have the diode, but you don't have any information on the diode. So besides using multimeter, you may also refer to the diode datasheet according to the specific code of the diode. Okay, there are cases when you might have to select a replacement diode when the type of diode needed may no longer be available. An example of a datasheet. Okay, this is the diode code that you have to know the concepts before you can see or look for a datasheet. Okay, this is the manufacturer, and these the table here are the characteristic. Okay, for example, this is the ratings. Okay, this is the thermal characteristic, how long it can withstand heat, and the rest. Okay, you can open an actual datasheet. Okay, this is another example of datasheet. Okay, this is the code. Okay, this is for the Zener diode. Okay, this is the manufacturer, and you have the electrical characteristic here. You can refer according to the type of devices under this code. Now we go to the Zener diode, a special purpose diode. Okay, the basic function of a Zener diode is to maintain a specific voltage across each terminal within given limits when line or load change. Okay, if we have variation of loads and variation of line, this diode will try to maintain a specific voltage value. Okay, so that means no wonder if you change the load, you change the voltage, the voltage across the diode will remain the same. Okay, typically it is used for providing a stable reference voltage for use in power supplies and other equipments. Okay, a Zener diode is much like a normal diode. Okay, first the positive part here is similar to a normal diode. Okay, the exception being is that it is placed in circuit in the reverse bias and operates in reverse breakdown. Okay, normal diode doesn't have this part, but for Zener diode it has this part. Okay, this is the specialty of the Zener diode because it can operate in the reverse breakdown until it can no longer hold the reverse breakdown value. Okay, this typical characteristic curve illustrates operating range for the Zener diode. Now that is forward characteristic is just like a normal diode. So this is the forward characteristic. Okay, and this is the reverse characteristic. I can say that this one is a characteristic. Okay, so repeat again. Okay, a Zener diode is a normal diode in the forward characteristic, but it differs from the normal diode in the reverse characteristics. Okay, the Zener diodes breakdown characteristics are determined by the doping process. Low voltage Zeners less than 5 volts operate in the Zener breakdown range. Those designed to operate more than 5 volts operate mostly in lunch break range. Okay, breakdown range. Okay, this is what we say as avalanche. It means that it throws down up to the rising value of IR. Okay, so that means uh, the more the value of Zener diode operates, okay, the longer it will reach this breakdown range. Okay, Zener are available with voltage breakdowns of 1.8 volt up to 200 volt. Okay, so that means 1.5 volts here. This is the voltage up to 200 volts. Okay, the illustrates the minimum and maximum ranges of current operation that the Zener can effectively maintain its voltage. Okay, what the value of Zener diode here? So when it is given high current value, it still maintain the value across the Zener diode. It means that the value in terms of the Zener voltage, the voltage across the Zener Okay, so one of the application is as a regulator. Okay, in this implementation of Zener regulation circuit, Zener will its impedance based on varying input voltages and loads to be able to maintain its designated Zener diode. Okay, because let's say this is the load voltage VL, L where VL equals to IL per L. This is the Zener diode, and this is what we say as a VZ, okay, the voltage across the Zener diode. Okay, if we use a Zener diode of 6 volt value, okay, and because it is arranged in parallel to VL, it will try to maintain the value of VL always 6 volt value. So whatever the value of V in and whatever the value of RL, the output value of the load value of 6 volt will always be maintained. The value used here is 6 volt. And if we have the value of Zener diode, for example, another value of 10 volt, it will also try to maintain VL at 10 volt also. Okay, Zener current will increase or decrease directly with voltage input changes, and the Zener current will increase or decrease inversely with varying loads. Again, the Zener has a finite range of operation. Okay, it's how it is calculated mathematically. Okay, I will move forward from this one. You can try to figure out the mathematical formula for this in order to determine the value of VL. Okay, another application is as a limiter. Okay, Zener diode can be used for limiting just as normal diode. Okay, so you have to recall in previous chapter about the limiters. Um, in terms of Zener diode also, the previous difference to consider for a Zener limiter is Zener breakdown characteristic. Okay, we have this configuration pointing upwards. We have this configuration pointing downwards. We can also have pointing downwards and pointing upwards. So it can limit current, it can limit voltage, and it can be used to clip away a portion of the waveform. Okay, similar as a clip as before. Okay, so we have another type of diodes. Beside the Zener, we have optical diodes. Okay, this is very famous, normally used for lighting a segment. So because of its characteristic, which can light up, it can be used to form a numerical display. Okay, we can display alphabet, we can display number. Okay, so this optical diodes is famously or generally applied or as a 7-segment display, SSD. Okay, I think you have learned this before in the digital subject. Okay, and we also have photodiode used to vary current by the amount of light that strikes. Okay, it plays in the circuit in reverse bias. As with most diodes, with when in reverse bias, no current flows when in reverse bias. But when light strikes the exposed junction through a tiny window, reverse current increases proportional to the light intensity. So that means the optical diode receive light and it will conduct. Okay, no light, no conduction. So it can be used as a sensor also, as a photodiode sensor. Another diode types, we have the current regulated diodes that keeps a constant value, current value over a specified range of forward voltage. Okay, for example, ranging from about 1.5 volt to 6 volt. Okay, and then we also have the Shockley diode. Okay, it is very similar. It's very significant characteristic is its fast switching speed and low forward voltage drop. Okay, so that means it has a low voltage drop compared to the normal diode. Remember again, For the silicon diode, we have 0.7 volt voltage drop, and for the germanium, we have 0.3 voltage drop. Okay, so for this Shockley diode, it can range from 0.15 to 0.45 volts. Okay, thus, this is very useful for high frequencies and digital application. It is not a typical diode that in fact does not have a p-n junction. Instead, it consists of a heavily doped metal bound together. Okay, so this is, remember again, this is a N-type, but there is no p-type. It is only metal. Okay, so that means there is no holes because there is no p-type. There is no holes here. Okay, so only N-type. So I will not discuss on this one. Okay, another one we have a pin diode, okay, which is also used in mostly microwave frequency application. Okay, it's variable. Okay, microwave frequency means that the frequency is very high. So that means this is a very fast switching applications. Okay, it's variable forward series resistance characteristic is used for attenuation, modulation, and switching. In reverse bias, it exhibits a nearly constant capacitance. Okay, so the difference between the normal diode is that between the P and N junction, there is what we call as intrinsic region. Remember again, intrinsic and extrinsic. Okay, intrinsic is the semiconductor material in a very pure state. So intrinsic is having poor conductivity. Okay, so if you recall back in the diode, whereby we have a P and N junctions, in the middle, in the boundary, we have the depletion region. So this one don't have the depletion region. Instead, we have intrinsic region. Okay, that's for your knowledge. Another types we have the step recovery diode, which is also used for fast switching applications. This is achieved by reduced doping at the junction. And we have also tunnel diodes, which has negative resistance. Okay, you can try to Google for the picture of the tunnel diode. And then we also have a laser diode, okay, which produces a monochromatic single light color. As the laser diodes in conjunction with photodiodes are used to retrieve data from compact discs. Okay, if you also nowadays, you can simply buy a laser pointer. Okay, a laser pointer is very small. So laser pointer in this case is produced by using semiconductor, and the cost is very cheap. You can simply buy uh, a laser pointer for a few ringgits. It's very cheap. So because the material is very cheap, it will use semiconductor to produce the laser from using the diode. Okay, so I will not go through the troubleshooting in power supply. You can have a reading on your own. So this is regarding the troubleshooting using the diodes. So I will stop until here. So that's the end for the chapter 2. Thank you very much.